All right, let's get into it. Today, we're going to pop the hood on a large language model and see what's really going on inside. We're going to deconstruct its brain, looking at the actual code that powers the whole thing. And we're starting with the most fundamental piece of the puzzle, the transformer block.
You've probably wondered this, right? How does an AI actually think? It can feel like this incredibly complicated, almost magical process. But here's the thing. It's not magic. Not at all. It's just some really, really elegant engineering. And the answers? Well, they're sitting right there in the code.
So if we want to understand how these massive models work, we've got to start small. We need to look at the one component that gets copied and pasted over and over again to create the AI's mind.
And that component is called a transformer block. The best way to think of it is like a single Lego brick. A really powerful, really smart Lego brick. An entire AI is built by stacking dozens, sometimes hundreds, of these blocks on top of each other. Each block takes in some information, chews on it for a bit, and then passes a slightly more refined version up to the next block in the stack.
Now, this is the most important part. This block is not some mysterious black box we can't understand. It's a piece of software. It's modular, it's configurable, and by looking at its code, we can see the exact decisions and trade-offs that engineers are making when they build these things.
Our investigation starts with the architectural blueprint. In the world of code, this is what's called the initialization method, or init. This is basically the set of instructions that tells the computer how to build one of these blocks before it's ever seen any single piece of data. And this one line of code is where it all begins. It's pretty simple, really. It's just saying, okay, to build a new transformer block, I just need two things. First, your unique number in the stack, that's the layer ID, and second, the master set of rules for the whole model, which we're calling args. This little detail means that every single block can be built a little bit differently, depending on where it is and what the overall design calls for.
So what gets built inside this blueprint? Well, there are three main parts. You've got the attention head, which is kind of like a spotlight that helps the model focus on what's important. Then you have the feed-forward network, which is really the thinking engine of the block. And finally, you have these normalization layers, which are basically there to keep all the data clean and stable as it flows through.
So let's zoom in on that first piece, the attention mechanism. Its big job is to figure out which words or which pieces of data are most relevant to each other. But to do that, it has to solve a really fundamental problem first. Yeah, how does the model even know the order of words? Think about it. The sentence, dog bites man, means something completely different from man bites dog. The attention part needs to know the position of every single word, and the blueprint has a pretty fascinating way of handling this. It basically gets a choice between two options. On one hand, you have ROP, which stands for Rotary Positional Embedding. This is the default, and it encodes the position of each word right into the data. But then you have this other option, NOP, or No Positional Embedding, and this one forces the layer to completely ignore the word order. So why on earth would you ever want to do that? Well, the code that makes this choice is really cool. It lets engineers set an interval, so you could have, say, every fourth layer be a NOP layer. This actually forces the model to learn relationships based purely on the meaning of the words, not just their sequence. It can make the whole model smarter and more robust. It's a totally deliberate design choice, and it has a huge impact. Okay, so the next major part of the blueprint is that thinking engine we talked about, the feed-forward network. This is where the real number crunching happens. And just like with the positional data, the AI architect has another big choice to make here. The question is, does one size fit all? Should every single piece of information get processed by one big, powerful, general-purpose engine? Or is it maybe better to have a whole team of specialists and just send the data to the right one for that specific job?
And that right there is the difference between a standard feed-forward network, or FFN, and a mixture of experts, or MO. The FFN is your generalist. All the data flows through it. The MO, on the other hand, is that team of specialists. It has a bunch of smaller networks, these experts, and a smart routing system that decides which expert is best suited for each little piece of data that comes in.
And you can see this choice perfectly in the code. This if-else statement is literally a fork in the road. Based on the rules, it just asks, hey, for this layer, should we be using a mixture of experts? If the answer is yes, boom, it builds an MOE engine. If not, it builds the standard feed-forward one. Just think about that. This means an AI can have different types of thinking engines at different depths of its own mind. So,
We've looked at the blueprint and all the components have been built. Now let's switch gears and actually follow a piece of data as it goes on its journey through the block. This part of the code is called the forward method. You can think of it as the assembly line where the real work gets done.
And this journey has 4 main stops. First, the input data gets cleaned up, or normalized. Then the attention mechanism does its magic, figuring out what to focus on. After that, the result gets normalized again, and finally, it's sent to that powerful feed-forward engine to get processed. Let's see what that looks like in the code.
Here are the first 2 steps, all in a single line. The input, which is called X, first goes through the attention norm layer to get cleaned up, and then it's fed right into the self.attention module. But look closely at the beginning. X plus ... The result of all that processing is then added back to the original input. This is called a residual connection, and it's absolutely crucial. It helps the network learn better by making sure it never forgets the original information it started with.
And what do you know? The final 2 steps look almost exactly the same. The output from that attention stage, now called H, gets normalized again with FFN norm. Then it's passed to our thinking engine, the self.feedforward module. And, just like before, the result of that is added back to its input. This whole normalize, process, add pattern is the fundamental rhythm of the transformer block. It's the heartbeat of the AI. So what this all tells us is that understanding for an AI isn't some single flash of insight. It's a process. It's about iterative refinement. Each block takes what the previous block figured out and adds its own new layer of understanding, refining the data step by step until a final answer can emerge at the very end. At the end of the day, what this code really shows us is that flexibility is the secret sauce here. The ability to mix and match these components, to tell one layer, hey, you, ignore word order, and tell the next layer you get a whole team of specialist engines, that's what lets engineers design these incredibly nuanced and powerful AI models. And that leaves us with one last thing to think about. If an AI's core cognitive parts can be configured and swapped out so easily on a layer-by-layer basis, what does that actually mean for the future of intelligence? It kind of suggests that the future isn't about finding one single master algorithm to rule them all, but maybe it's more about becoming a master architect, someone who can skillfully assemble lots of small, elegant, and interchangeable parts. Something to chew on. Thanks for diving into the code with me.